I am a teacher at the Center for Advanced Technical Studies in Chapin, and I teach pre-engineering classes there. In my classes, students are exposed to lots of engineering and physics concepts, and they are expected to be able to solve real-world problems. Last year, I stumbled on an approach that has dramatically changed the way I teach those engineering concepts. The method makes it easier for me and students to understand the problem and to also be able to show the level of complexity of the problem. Before I tell you about the technique, I'd like to take you on a journey of how I arrived. Recently, I moved and found a high school report card with comments from a guidance counselor interview. It said I stated, "I like to make things work. I like to make machines run." It was recommended that I pursue engineering in college. That was in 1977. In my second year of college, I remember the pleasure I had in developing computer programs and how I liked helping others with their programs in the Programming for Engineers class. I could make the computer do what I wanted it to do. I could make things work. The thought even passed through my head that I could teach topics like computer programming in a high school. Where did that come from? I never gave it a second thought. College was not without struggles, however. Word problems were in every class. I would eventually get them, but often I felt as if I was blind or inside a forest walking around in circles. I eventually got better by my senior year. I did enjoy college, however, so much that I stayed all the way through a PhD, which was paid for with a teaching assistantship. I helped teach freshmen how to use the computer and make things work. Working with students made me ask the question, how do people learn? For the next 14 years, I worked as a designer, project manager, engineering manager, author, consultant, making things work. But in 2002, a change took place. I switched careers to become a high school teacher, 23 years after having had the thought about it in an engineering computer lab. In the process to become a high school teacher, the question of how people learn would get its due. In the course of becoming a teacher, I learned that the most difficult learning is that which has no previous foundation to build upon. The easiest learning is when a framework of knowledge already exists for the new concept to be hung on, and the technique I am presenting is in this category. Solving a problem has often been described like solving a puzzle. You have to make the pieces fit together. But what are the pieces, and how do they fit together? To solve a puzzle, you usually start with the corners. There's only 4 of them, and they're easy to find. Next, you look for the side pieces. They have the straight edges. And then finally, you look for the parts in the middle by matching up the shapes of the other pieces and the images. These steps are precisely what takes place when planning out a math word problem. Solving a math engineering word problem requires a scope of knowledge that consists of the physics principles expressed in math equations and sometimes some specialized vocabulary. The pieces of the puzzle are the physics principles. They relate variables to each other. If you tell me the width of a rectangle, I can tell you its perimeter and its area. At the planning stage to solve word problems, the actual equations are irrelevant. Only the quantities that are related matter at this stage, such as length, width, and area. The corners represent the given and the results to be found. These are typically easy to find. Edges are those relationships that connect directly with the given or the required results. And then finally, the pieces in the middle are those that connect the other pieces together. Let's look at an example problem. Given a perimeter of 18 feet and a length of 5 for an enclosed rectangular space, determine the area and the width for the space. Okay, our foundation pieces or our puzzle pieces represent the perimeter of a rectangle and the relationship of the area of a rectangle. Perimeter relates variables P, L, and W, and area relates A, L, and W. Our first step is to find our corner pieces. Those represent our given and find. We are given perimeter of 18 feet and a length of 5 feet. We're asked to determine or find the area and the width for the space. Next, we find the pieces that directly relate to our given and our finds. Okay, in this case, you can see the perimeter equation, which has perimeter. Okay, we can connect that and then our length, which we can also connect. Okay. For our area, area is one of our finds. Now, here's a rule about using these. You only have one output, and you have basically however many variables minus one inputs. When those conditions are met, you know you can solve the problem. Finally, we're looking for the internal pieces, and those are the pieces that connect together. Given perimeter and length, we can find width, which is one of the given values that we need to calculate area. From the very beginning, we've been given area, so we can connect that. With these two found, we know we can calculate area. Finally, width had actually been solved back here, so we can do this. We can see that we've mapped out the problem and we have a solution path. To actually get the answer, however, you actually need to do the math. So let's take a look. Here's P for perimeter of 20 feet. L is our 5-foot length. We substitute into the appropriate width equation and come back with a width equal to 4. Using this found width along with the given length of 5 into the area calculation, we calculate our area, giving us final results, area 20 feet, square feet, and width 4 feet. In this example, we've used cards. Those students who like to work with physical manipulatives, this is a great approach. But another approach is for students who like to draw, they can simply draw these boxes and relationships. Here's another simple problem. Okay, given the perimeter of 18 feet and the area of 20 square feet for an enclosed space, find the length and width. In this case, we have the same pieces. Our given perimeter, we can hook up to the perimeter relationship. The area, we hook into the area. But notice what we're looking to find, length and width, are two variables, but we have two equations. That's a system of equations. So this approach, putting this box around it, tells us you need to solve the system of equations and you can find the answer. Now, that in itself represents a whole scope of learning. One approach is to graph two equations and see where they cross. The cross points become the solution. So rewriting the perimeter equation to find width and then rewriting the area equation to find width, we can substitute a number of values, plot the curves, and where the curves cross are solution points. And notice here's our solution, 5 and 5, 4 and 4. The two curves are crossing. It says we have one solution with a length of 4 and a width of 5, or a length of 5 or width of 4. These represent two possible solutions. Now, this approach allows you to see how to go about solving a problem and what techniques are available. But it actually does something also. It helps with learning some techniques that are actually very valuable for engineering. Here is an example of a programming environment called LabVIEW. LabVIEW, you actually get to connect fields using wires to be able to show the interconnections. In the lower left-hand corner is breadboarding. Breadboarding, you physically connect components to be able to make a working circuit. I hope you found this presentation useful. Okay, if you'd like to find some videos and resources, please go to my website at tinycc/wordproblem. Thank you.